Okay, so we've got a torsion problem that we want to solve today. So it's a step shaft, if you will, between A and D. It's fixed at both A and D. So we have a narrower component between A and C made out of aluminum, and a somewhat thicker component between C and D made out of steel. And we have torques applied at B and C as shown in the diagram. And all the key material properties and dimensions and everything are either shown in the diagram or given in the problem statement. And what we want to do is we want to go on and figure out what the reactions are at both A and D, and get a torque force diagram drawn in kilonewton meters for the entire bar, as well as then we're going to go on and look at the maximum shear stress within the bar and figure out where that's going to occur. So we can do that. And then finally, we're going to figure out what the angle of rotation is at point C and draw the angle of rotation diagram for the entire bar. So quite a lot of work. I'm sure we're not going to be done in 5 minutes. It's going to take us a little bit to get through it all. But we should be able to do it fairly quickly. So I guess the first thing I want to do is I'm just going to do a couple preliminary calculations so that we have them available to us later. So preliminaries. And by that, really what I'm talking about in this case is I just want to get my polar moments of inertia for the two cross sections. So the aluminum cross section then, of course we know it's pi d to the fourth over 32. And so that's pi times 60 millimeters, all to the fourth divided by 32, and that gets us a value of 1.272 times 10 to the 6 millimeters to the fourth. And we'll do the same thing for the steel. And that's 80 millimeters. And gives us 4.021 times 10 to the 6 millimeters to the fourth. Yeah, and so with that done and out of the way, then we can just use those values and plug them in as we need to later on. So that's going to be useful to have. And other than that, we're going to start this the same way as we do just about every problem. We're going to pop over to the left and do a free body diagram and then work our way down. So let's get that started. So we have a free body diagram. It's labeled. I'll put in my reactions. And so we have a torque reaction or potential torque reaction at A, and another one at D. We'll get those labeled. So that's, I just called it reaction at A, reaction at D. And then we have our externally applied torques. So we have one at B. Oh, that's not working that well. And then we have one at C. Get those labeled in. So that's 1.0 kilonewton meters and 1.5 kilonewton meters. Let me think, what else do I need to do? I should identify our axis X. And for the most part, I think that's it. We have our dimensions are carrying down from the diagram above, so we should be good. Now, the one thing that I note right away, which hopefully you have, is with this fixed at both A and D, it is a statically indeterminate problem. We only have one equation of static equilibrium, which is the sum of the torques about the x-axis. And we have two unknowns, therefore it's statically indeterminate. So I'm going to use superposition to solve this. So we're going to break it up into a primary and a redundant system. And of course we know that the prime or the free body diagram of the full system is equal to the sum of the primary and the redundant systems. And so I'm going to choose the reaction at D to be my redundancy. And so on my primary system then, I'm going to have a reaction at A, and I'll give it a prime to denote that it's not exactly R at A, it's just the reaction at A in the primary system. And then I will put my externally applied torques on. I'll put both of them on here. And that's 1.0 kilonewton meters, 1.5 kilonewton meters. And I'm not going to put the reaction to D on because that's my redundancy. And so now I can go down and do my redundant system. And so again, I have a reaction at D, and that will get a double prime to denote that it's the redundant system. I don't have to put my externally applied forces on, but I do need to apply my reaction at D as if it was an externally applied force. And so that will be my reaction at D. And when I look at all of the forces, I can see that the redundant system plus the primary system adds up to be my original system. And the other thing I want to note is here, when I look at deflections at the end, so this will be an angle of twist at D double prime. This is going to be an angle of twist at D single prime. And this is going to be the angle of twist at D, which has to be equal to 0. It's also equal to the sum of the angle of twist at D prime plus the angle of twist at D double prime, which is what's coming up next, because what's next is we need our compatibility equation. And that comes from those systems and the displacement specifically about those systems. And so we have our angle of twist at D is equal to 0, which is equal to our angle of twist at D prime plus our angle of twist at D double prime. And with that, that's going to be the extra equation that allows us to solve this. Now, let me think, where do I want to do? So just as a reminder, our angle of twist between any 2 points is equal to the sum of T at I, L at I, J at I, G at I. And so we're going to be able to substitute terms for the angle of twist into our compatibility equation and then be able to solve this. So the first thing I want to do is I want to go back to my primary and redundant systems, and I want to do, almost mentally, to be fair, a method of sections. And so if I start on my redundant system, we see that there are no torques applied between A and D, which means that you're going to have the same torque applied all the way between A and D. So if I do a single method of sections and I look only to the right, so I get rid of everything to the left because I don't know what our D double prime is, but I do see over the right, all we have is our D. Now I want to give kind of very quickly, RD is on a positive face and it's going in the positive X direction. So RD should be the internal torque as a result of RD should also be positive. Now I'm going to go up to my primary system. Now I see there's 3 different sections that could have different torques. So the first one is over here between C and D. And again, if I get rid of everything to the left of my cut and look just to the right, there's nothing applied. So I know that I'm going to have a 0 torque, internal torque between C and D. Now I'm working my way left. And so over here, between B and C, again, get rid of everything to the left, look only to the right, and I see that I have 1.5 kilonewton meters, but it's going in the negative direction on a positive face, so my internal torque is going to be negative 1.5 kilonewton meters in that section on the primary system. And we'll do the same thing one more time. So we end up adding these together, and I have 0.5 going to the left, which would be a negative 0.5 kilonewton meters. Again, working only in the primary system. And so with that, I know what my internal torques are within my primary and redundant system. And so I have pretty much everything I need to plug into this equation. So what I'm going to do is I'm going to set this up and say, okay, this is equal to my torque between AB, length between AB, J of the aluminum, G of the aluminum, and to that we will have to add the torque between BC, length BC, J aluminum, G aluminum. Now all of that makes up the totality of phi d prime. And we don't have to do section CD because there's no torque, it's 0, so that's going to cancel that out. And so to this, following along my compatibility equation now, we have to add phi d double prime using the same equation. So we have only a single torque, but we have two different sets of geometric and material properties, the aluminum and the steel. So we're going to have to break it up into two terms. And so I'm going to add to that, and our torque we know is RD. Oh, I should do the generic first. So we have our torque AB, length AB, J aluminum, G aluminum, and then we'll do BC, length BC, all over J aluminum, G aluminum. Now in this case we're working off our redundant system, so this represents phi d double prime, and we'll take our values from the redundant system. And so now we're ready to plug in some values. Okay, so our torque AB, we said, is negative 0.5 kilonewton meters. Now I want to work in newtons and millimeters so that I can deal with megapascals. So I need to multiply by 10 to the negative 6. So if I go, that's equal to negative 0.5 times 10 to the negative 6 Newton millimeters, times our length AB was 150 millimeters, all divided by our J of the aluminum, which we calculated previously as 1.272 times 10 to the 6 millimeters to the 4th, and our modulus of rigidity for the aluminum, 27 gigapascals, or 27,000 megapascals. And now we'll go on and do our torque BC again on the primary system, so negative 1.5 kilonewton meters, or negative 1.5 times 10 to the 6 Newton millimeters, a length of 150 millimeters, and the same, we're still in the aluminum, so these will be the same, millimeters to the 4th, 27,000 megapascals. And then we transfer to the redundant system for the last two terms, and so we go plus, our torque is RD in both sections, so it's RD, and our length is 150 millimeters divided by 1.272 times 10 to the 6 millimeters to the 4th, 27,000 megapascals. And to that, we look at the next one, and we have torque BC. So that again is RD. And our length, oh no, it's not BC. Oh, and it's not aluminum either. Okay, so let's go back and fix this. Some of you guys probably noticed this and you're wondering if I was going to keep messing this up. So this is, we made one other mistake. So this is, let's go back. So this is the torque between AC, the whole length, times the length AC. And so the torque, the torque is fine, but the length here is 300 millimeters. Okay. And then this becomes the torque CD, and this is steel, and that is steel. So we have RD, and our length is 400 millimeters, divided by 4.021 times 10 to the 6 millimeters to the fourth, and 75,000 MPa. Okay, so that was a little bit painful. We had to go back and fix it, but hopefully we see that. And so those last two terms are all from the redundant system. The one is the torque in the aluminum, the whole aluminum section, A to C, and the second part is the torque RD in the steel section, CD. And so with that, we can actually, you'll see we have, and that's all equal to 0. So we have one unknown. We can isolate for RD, and we get a value of 0.868 times 10 to the 6 Newton millimeters, or 0.868 kilonewton meters. And we can go mark that up here, so we know that RD is 0.868 kilonewton meters. Okay, so having done that, that's really the hard part. So let's keep going along. So now we want to do our statics to solve for our A. So that would be sum of the torques about the x-axis is equal to 0, and that's equal to our RA plus 1 kilonewton meter minus 1.5 kilonewton meters plus RD, which we now have a value of 0.868 kilonewton meters, and we're able to get a value of RA is equal to negative 0.368 kilonewton meters. And so with negative, we understand that we're actually just going the other direction from the direction that we assumed when we drew our picture. So I'll put that in our free body diagram. So now we have the first part done. We have our reactions. Let's just annotate some stuff here. And so now we want to do our torque force diagram. And so we're working from our free body diagram. And let's put our torque force diagram down here. We're going to work in kilonewton meters. So we'll label it here so I don't have to carry it on. And so we have RA. It's actually going to the left. It's showing as right, but it's a negative. So it's 0.368 kilonewton meters to the left, on a negative face. So when we do our method of sections and we cut it, the internal torque is going to be going to the right 0.368. So that would be positive. So that's how I'm going to get my sign. So we're going to go up to 0.368. And then we go across. It's constant between there and where the 1 kilonewton meter is. And so that's to the right, so that's going to draw us down to negative 0.632. So we're just subtracting 1 from the 0.368. That goes across, and then the 1.5 is going to push us up to a value of 0.868, and takes us across, and then our reaction brings us back down to 0, which is a good indicator that we might not have made a mistake. So we've got, let me just look at the problem again. So we have our reactions, we have our torque force diagram, it's done in kilonewton meters for the entire bar. So part B then is looking for shear stresses. So let's get that set up. I'm just going to give myself a little bit more room. Okay, so I've given myself a little bit more room. And now I need to work on shear stresses. Which is a tau. And so we're not quite sure. So we want to know where it is a maximum. So we don't really know whether that's going to be in CD or somewhere between A and C, because we have different torques and different dimensions or different radii. So if I were to look at it and I look at the torque force diagram, so the absolute value magnitude is largest between B and C. So it could be between B and C. It's not going to be between A and B. It would either be between B and C, or it could be between C and D. We're not quite sure. So we're going to have to test both of those. So let's do that. So the shear stress between B and C is equal to our torque between B and C, our radius, R, divided by our polar moment of inertia, J, and that would be for the aluminum, and the radius would be for the aluminum. And so when we look at the torque, we see that that is negative 0.632, and we can put it in as negative. That's just going to change the direction that it's going in this case, but we'll keep it in. So negative 0.632, but we're going to multiply that by 10 to the 6 to put it into Newton and millimeters. And our radius we're going to put in as 30 millimeters, and divide that out by J, which is 1.272 times 10 to the 6 millimeters to the 4th, and that's going to be equal to negative 14.90 megapascals. And then we have to check our shear stress between C and D. So we're going to go tau CD, T CD. This is the radius of the steel and the polar moment of inertia of the steel. And so we'll put in our values. So that's 0.868 times 10 to the 6 Newton millimeters times our radius, which is 40 millimeters. And that'll be divided by a larger polar moment of inertia, so 4.021 times 10 to the 6 millimeters to the 4th. And when we calculate that out, we get a value of 8.63 megapascals. And so we can see from that that the maximum shear stress is going to happen between BC. So that's tau max. And I'm just going to take a note. This happens between B and C at outer fiber to indicate where it's occurred. Now, if I go back to my problem, so that does everything we needed for part B, and then it asks us to calculate the angle of rotation at point C in degrees, very specifically, and draw the angle of rotation diagram for the entire bar. So let's do that. So we're going to look at displacements, or angles of twist. Displacements. And so the angle of twist between A and B is equal to our torque between A and B, length AB, all over J. And we're still in the aluminum here, G aluminum. And we can go ahead and calculate that. So I'm going to 0.368 times 10 to the 6 Newton millimeters times 150 millimeters is the length, and then our J aluminum 1.272 times 10 to the 6 millimeters to the 4th, and our modulus of rigidity 27,000 megapascals, and that gives us a rotation of 0.00161 radians. And then we need to do our phi BC, so the angle of twist between B and C. They're all relative. So that's our torque BC, length BC, J, we're still in the aluminum, G aluminum, and so you get negative 0.632 times 10 to the 6 Newton millimeters, and a length of 150 millimeters. And 1.272 times 10 to the 6 millimeters to the 4th, and the modulus of rigidity, 27,000 megapascals. And we get a angle of twist between B and C of negative 0.00276 radians. So the angle of twist between A and C is angle of twist AB plus angle of twist BC, and that's going to be equal to 0.00161 radians minus 0.00276 radians. That gets us a value of negative 0.00115 radians, and I'm going to multiply that by 360 degrees per 2 pi radians, and that's going to get us an answer in degrees of negative 0.0659 degrees. And phi, and that is also the phi at C, because phi AC is the same thing as phi C, because the phi at A is equal to 0. So I can write that down as phi C. So that answers that question. Now we want to do the diagram, and this is why I did it out in 2 distinct steps between A and B and C, because I anticipated that I was going to be doing the diagram. And so if I go back to the diagram, so let's get it labeled. So angle of twist, and I'm just going to do it in radians. Doesn't specifically say in the problem what the diagram is supposed to be. And so if I were to do that, I can go straight line out here, and we calculated a value of 0.00161 radians. And then we got the angle of twist at C was down here. and that had a value of negative 0.00115, and then of course it goes back to 0. And you could also just calculate the angle of twist between C and D, and of course that should be a good check to bring you back to 0. I haven't done it here, but it wouldn't be a bad thing to do at all. And so that fully answers the problem. So let me just bring up the whole problem sheet here. We can see it done out. We've answered everything they asked for. We used the method of superposition to get our compatibility equation, which allowed us to get the reactions. From there we got a torque force diagram with the internal torques. Now we're able to look at displacements and stresses. And so we've got all that they have asked for. So hopefully that was helpful. And we'll see you at the next problem we have.